We're going to continue the notion of infinite limits and also introduce the concept of limits at infinity, which we haven't looked at yet. So previously we did a problem where we wanted to find the limit as x approached a number, and when we plugged it in, we got 0 in the denominator and we could not factor it out or multiply by the conjugate, so we used the table. And what the table showed us is that as the x was approaching the number from the left and from the right, the y's was doing something very specific. It was actually getting very large or very small, so it was going to positive infinity or negative infinity. And actually when this happens, it creates a concept that's very important in a graph. It's called a vertical asymptote. So here's the mathematical definition of a vertical asymptote. The vertical line x is equal to a. It's a vertical asymptote for the graph y is equal to x if your y's go to infinity or negative infinity as your x approaches a either from the left or from the right. So at a vertical asymptote, your graph has to at least do one of these four things, which I'll draw on the side here. So if I have a vertical asymptote, I'll just hypothetically put it here. One of these behaviors have to occur, and sometimes more than one will occur as long as your graph still passes the vertical line test. So either it will come from the left and your y's will go to negative infinity, or it will go from the left and your y's will go to positive infinity, or your x will approach from the right and your y's will go to negative infinity, or it will approach from the right and your y's will go to positive infinity. But this is the behavior of a vertical asymptote, and this is what the table showed us. And so when this happens, you know that you have a vertical asymptote, and visually here you can see it. So what I've done here is I have a problem where we're going to take this rational function graph. F of x is equal to x squared minus x minus 2 over x squared minus 4. And again, this is a rational function because it's a polynomial divided by another polynomial. And I want to look at two different limits, as x goes to 2 and as x goes to negative 2. So again, because this is a rational function, the first thing you always want to try is you do want to try to plug in. So I have the limit as x goes to 2, and I'm going to plug it in of f of x, and then I'm going to plug it in. So I have 2 squared minus 2 minus 2 over 2 squared minus 4. And at the top, I'm going to get 4 minus 2 minus 2, which is 0. And at the bottom, I'll have 4 minus 4, which is also 0. So this is undefined. So the next thing that I want to do is I want to try to go to one of my go-tos. I want to try to simplify it, factor. So I'm going to have here the limit, as x goes to 2, and let's see if this factors out nicely for us. This will give me x minus 2 times x plus 1 over x minus 2 times x plus 2. Don't forget to check your factoring by FOILing, very important. And here something magical happens, the x minus 2's do cancel. So what I'm left with, right, don't forget to always write your limit because I'm not done taking it. I haven't taken the limit yet, I've just manipulated the function. So I have x plus 1 over x plus 2, and now I can try plugging in again. And that will work because the issue was with the x minus 2. And so this is going to give me 3/4. So what this actually tells me is that the function has a hole there. All right, the function does not exist at x equals 2 because it's undefined there. But as your x is approached to, your y's are actually approaching a number, 3/4. So what will happen is it will look like this, right? You will have 1, 2, and what happens is at 2 3/4 you will have a hole, but your function will still approach the 3/4 from both sides. Now let's take a look as if we're taking the limit as x goes to negative 2. So we have the limit as x goes to negative 2. So again, you would try to plug in. So you would have negative 2 squared. Make sure to use those parentheses properly. Minus minus 2 minus negative 2 over negative 2 squared minus 4. So we're going to have 4 plus 2 minus 2. And here we're going to have 4 minus 4, which is going to give us 4 over 0. So that's still undefined, right? But we want to, again, try to manipulate, try to factor, which we have already done, right? We've already factored. We have the factored form of the function right up here. But now we're taking the limit as x goes to -2. And if I try to plug that into the factored form, unfortunately, I'll get -2 plus 1 over -2 plus 2. So that will give me -1 over 0 still. Now, what this is telling me now is that the function has a vertical asymptote there. All right, because when I put in -2, even in the factored form, it is still giving me a 0 in the bottom. So what we're going to try to do, or what we have to do now in what we did in the previous problem, is to use a table. So I will help you set up your table, and then you can use your calculator to kind of find the points on your own. So you have x and y, and then you would have -2 in the middle here. And then you're going to pick numbers from the right and numbers from the left. And you know, right, you could do -1.9, -1.99, -1.999, and so on. And then from the left, you could do -2.1, -2.01, and then just get closer and closer to it. Now, I'm going to provide a visual for you, which in calculus, right, we'll actually be working on graphing these and finding more information about the graph. You do learn how to graph rational functions in algebra, but it might have been a while for some of you. So what happens is here, right, we are going to have a vertical asymptote at -2, which the table is going to show you that by the definition of the vertical asymptote. You will also have a horizontal asymptote at 1, y equals 1, and we'll talk about that in this section actually. So I also have a y-intercept at 1/2 when I plug in x equals 0. And if I set the function to 0, I will get an x-intercept at -1. So what my function actually does, and don't forget you will have a hole here at 3/4, which I already did a small diagram, your function is actually going to look like this. And you can use a graphing tool on the internet to get an even better visual, because I'm freehanding this. And on the left, it's going to look like that. So what you will find, and your table will show you this, is as you're plugging in points from the left of -2, your graph is actually going to shoot up. The numbers are going to get really, really large. So you have that the limit, as x goes to -2 from the left of f of x will be infinity. And then as you plug in numbers on the right of -2, you're going to see the numbers are going to get extremely small. So you're going to have the limit as x approaches -2 from the right of f of x, that's going to go to -infinity. And again, what this tells me is it tells me the definition of the vertical asymptote. That's the behavior of the asymptote. If your x approaches from the left or from the right and your y's go to infinity or -infinity, then you have a vertical asymptote. So at x is equal to -2, you have a vertical asymptote. And at x equals to 2, because you were able to cancel out, you have a hole. Now, keep in mind here, because the limit from the left was infinity and the limit from the right was -infinity, the actual limit as x goes to -2, which was what we originally were trying to find, does not exist because they are not the same. Okay, let's take a look at this problem here that I have next, which is a different type of function. I'm being asked here, does f of x is equal to 3 over x squared plus 1 have any vertical asymptotes? So the reason I'm asking this next is because, again, the holes in the vertical asymptotes are coming from when the bottom is 0, when the denominator is 0. So what you want to do here is, if it has any vertical asymptotes, it will come from the bottom. So you take a look at your x squared plus 1, and you try to find your zeros of your denominator. But if I try to do this, I get x squared is equal to -1, and that is never true. That's an imaginary number. And here we're in a function. We're talking about real numbers. So in this case, because you have no zeros in the bottom, you will have no vertical asymptotes or holes. And I just wanted to provide you these examples to remind you that a rational function does not have to have a vertical asymptote or a hole. Okay, so next we're going to introduce the notion of looking at when the x's are going to infinity or positive infinity. So we have this definition here. Let k be a positive real number, and x of k is a real number for negative values of x. And I'll explain in a little bit why that second part is important. And we have these two limits. The limit as x goes to infinity of x raised to the k will either be infinity or negative infinity. And the limit as x goes to negative infinity will do the same. Now the question becomes, how do I know if it's positive infinity or negative infinity? So I have two examples here, and I want to find the limits of these two graphs visually. So first I have, and I picked two very basic graphs. I have x squared and the square root of x. So x squared is the parabola that opens up like this. I'll do a rough sketch. And it's important to remember that x squared is a polynomial, so it has domain all real numbers. You can put in any x and square it. However, when you do the square root of x, because of what we just talked actually above in the previous question, the domain is not all real numbers. You cannot put in any negative numbers. So it starts at 0 and then it goes this way to infinity. And so that's why that part at the top there was important, that it says that the limit can only be taken if it actually exists, right? So if you have x to a power, if you have a root, an even root, square root of x, the fourth root of x, the sixth root of x, you cannot put in any negative numbers value of x. So in that case, the limit would not exist. Okay, so you have to keep in mind of the domains, of course. So if you want to find the limit here as x goes to infinity of x squared, well, visually, it's easy to see what happens. You're here. As your x's are going to go to infinity, your y's are just going to keep getting huge, because as you putting numbers and squaring them, your y's are also getting much bigger. So the limit as x goes to infinity of x squared is also infinity. And then here, if we take a look, the limit as x goes to infinity of the square root of x, and then here we're here. And even though the square root of x, right, the square root of 9 is 3, the square root of 16 is 4, even though the y's grow slow, they will get bigger and bigger and bigger, all right? So they will grow much slower than x squared, but they will grow. And eventually, they will keep going up, and so you will have infinity. Now, the one thing, and this question didn't ask you for this, but I do want, again, to reiterate the fact that here, the limit as x goes to negative infinity of the square root of x does not exist, because the domain, right, does not exist on the left side of the graph. However, for x squared, the limit as x goes to negative infinity of x squared, that will be up here, and your y's are still growing, because when you square something, it stays positive. So it's still infinity. So let's kind of summarize what's happening on the left-hand side of the graph here. So to find the limits as x goes to infinity of negative infinity of polynomials, you actually look at the end behavior of polynomials. So as a little bit of a review from algebra, how does the end behavior of polynomials work? And so what happens is you actually want to look at the power functions of polynomials. Now, power functions is if you have y is equal to your coefficient and x to a power, I'll call it n. Okay, and this is a polynomial, so that n would be a whole number, positive. So you will have four different options, and keep in mind in your head of the two power functions for polynomials that we work with a lot. The first one is the one I graphed in the previous page, which is x squared. Oh, that was a horrible x squared. Let's try that again. And the other power function that we work with a lot is x cubed, and that function works like this. So because you have four options, the reason for that is because you have two options for a power. Either your power will be even or your power will be odd. And then the other two options come from the leading coefficient, which is the a, and either the a can be positive or the a can be negative. So your first option is that n is even and a is positive. So what happens there is, think about x squared. The end behavior of x squared is that it starts off in the top and ends also at the top. Now, what happens if a is now negative, the leading coefficient? Well, remember that putting a negative in front of a function reflects it vertically, right? So what will happen is that actually it will now go down and down. So that's what happens anytime the behavior, the power is even, and then both up if it's greater than 0 for a leading coefficient, and both down if the leading coefficient is negative. Now, if it's odd, the power, then you think about x cubed. So for x cubed, it starts down and ends up. Of course, this is for when your leading coefficient is positive. And if your leading coefficient is negative, it will do a vertical reflection of that. So it will start up and end down. So we're going to use that to find the limit as x goes to infinity or negative infinity. So I have two different examples here. So the first one is we want to find the limit to both infinity and negative infinity for the following functions. Now, where does your end behavior come from? Your end behavior comes from the leading term of your polynomial. The leading term is the term that contains the highest power, the degree of the polynomial. So if I take a look at this function, f of x is equal to negative 4x squared minus 3x squared minus 1, the leading term is negative 4x to the fourth. And that will tell me the end behavior of my graph. So because it's even, it will be like x squared, but it has a negative, so it will be vertically reflected. So it will be down and down. That means that the limit as x goes to infinity of f of x is equal to x. Well, if x goes to infinity, the y's shoot down, so it's negative infinity. And the limit as x goes to negative infinity of f of x, well, on the left-hand side, it still shoots down, so it's going to be negative infinity. Okay, let's do one more, and maybe you want to pause and try this one on your own and then check. So I have my leading term is 3x to the fifth, so it's going to be like x cubed, and the leading coefficient is positive, so it's going to stay like x cubed, down and then up. And so I have that the limit as x goes to infinity of my, oh, not f anymore, it's g. Well, it shoots up on the right. So as the x's get bigger, the y's will get bigger. And you can see that, right? Because if you're plugging in really big x's into 3x to the fifth, it goes really big. And then you have the limit as x goes to negative infinity of g of x. And then your graph shoots down, because when you put in a negative number to a power of 5, it stays negative. And then you multiply it by 3. So it will also be negative infinity.